Welcome to this explainer, where we're going to demystify the foundational building blocks of cryptography. Now look, if you're a developer, you already know that trying to decipher documentation and mysterious error messages from security libraries can be, frankly, incredibly frustrating. I mean, there is nothing quite like a generic signature exception completely ruining your Friday afternoon when you're just trying to get two microservices to talk to each other. But it really doesn't have to be this way. Today, we are going to break down these core concepts without getting bogged down in complex, impenetrable mathematics. The goal here is to build your fundamental intuition about message integrity and authentication so you never get stuck, and more importantly, so you never find yourself blindly copying and pasting security configurations from a random blog post ever again.
Okay, let's take a quick look at our agenda. We'll start with the goals of cryptography, move into cryptographic hash functions, discuss the active tampering problem, introduce message authentication codes or MACs, and finally wrap up with securing data with HMAC. So I want you to think about this question for a second, because this single question sets the absolute stakes for our entire scenario today. How do you actually know the data your app just received wasn't altered? Because blindly trusting incoming messages or data payloads across a network is just a recipe for a catastrophic security breach. If an attacker gains access to the network infrastructure between your microservices, they can easily intercept, modify, and forward network packets in transit. They can literally impersonate trusted internal services and manipulate your backend systems at will, altering database records or financial transactions. To prevent these kinds of devastating breaches, we have to deeply understand the exact tools we have at our disposal to verify every single byte of data we receive.
So let's kick things off with Section 1, the goals of cryptography.
Every security tool we discuss today will solve one or more of these four exact problems. You can kind of think of this as our mental rubric for the rest of the explainer. First, integrity. This ensures data just hasn't been tampered with. It means a payload didn't lose or flip a single byte during transmission. Second is authentication, which confirms sender identity, basically proving an API request really came from your internal billing service and not, some rogue laptop on the network. Third, confidentiality. This ensures data privacy through encryption, so unauthorized parties just see absolute gibberish. And finally, non-reputation. This one provides legally valid, mathematically undeniable proof that a sender cannot deny sending a specific message. Now, understanding the nuance between authentication and non-reputation is absolutely vital here. Authentication means you, internally, know who sent it. Non-reputation means you can prove to a third-party judge or an auditor that they sent it, which usually requires a specialized digital signature. So keep these four distinct pillars firmly in mind as we go forward.
Moving right along to Section 2, cryptographic hash functions.
The crucial point to understand here is that a hash function is entirely deterministic. The exact same input file will always flawlessly produce the exact same output string. Even the tiniest change in the input data, like changing just a single capitalized letter to lowercase, will radically alter the entire resulting hash value. These functions are also strictly one-way. I like to think of a hash function like a mathematical meat grinder, right? You can put a steak in and get ground beef out, but absolutely no amount of processing will turn that ground beef back into a steak. You just cannot mathematically reverse the hash to retrieve the original data. Furthermore, they are collision resistant. Because there are infinite possible inputs, but a finite number of outputs, collisions logically must exist somewhere. However, a strong cryptographic hash makes it incredibly difficult, basically computationally unfeasible, to find two different inputs that produce the exact same hash in our lifetimes.
To make this concrete, let's look at Maven Central. It's the Java community's massive repository for open-source libraries, hosting millions of software artifacts. Now, data corruption happens all the time in large distributed systems, simply due to random network timeouts, dropped packets, or failing disk drives on edge servers. Because of this, Maven Central distributes cryptographic hash files alongside every single library download. When your build tool downloads a software package, it doesn't just blindly trust that the download was flawless. It actually calculates the hash of the downloaded file locally on your machine, and then automatically compares it against the hash file provided by the Maven server. If your local calculation matches the server's hash, boom, your file's integrity is perfectly intact. If they differ even slightly, the tool knows the download was corrupted, and it just immediately retries.
However, there is a serious catch when you're selecting your algorithms. While massive repositories might still host older MD5 and SHA-1 hashes for legacy backward compatibility, you absolutely must avoid using them for any new applications. Over the years, thanks to Moore's Law and vastly increased computing power, security researchers have successfully demonstrated collision attacks against both MD5 and SHA-1. This means malicious actors can now intentionally craft two distinct files that yield the same hash, completely breaking that integrity guarantee we just talked about. You should really only be using modern algorithms like SHA-256, SHA-512, or the newer SHA-3 family. Furthermore, because algorithms inevitably degrade over time as computing power increases, you should always design your software to allow for seamless hash function changes. A great best practice is adding an explicit algorithm version field to your JSON payloads or database schemas, something like #version equals SHA-256, so you can smoothly upgrade to a new standard 10 years down the road without breaking your entire application.
Which brings us to Section 3, the active tampering problem.
Now, here is the terrifying twist in our security architecture. While hashes brilliantly catch accidental corruption, they fail completely and utterly against active tampering. Imagine a man-in-the-middle attack. Alice sends a file and a hash to Bob. But a hacker, let's call her Eve, intercepts this transmission. Eve doesn't just read the data. She maliciously changes the payload entirely. But Eve knows Bob is going to check the hash. So because the hash algorithm is public, Eve simply runs her newly altered payload through that same hash function, politely generates a brand new, perfectly matching hash value, and forwards both the tampered file and the forged hash over to Bob. Bob receives the package, checks the new hash against the new file, sees that the math works out perfectly, and happily processes the malicious data, completely unaware that Eve compromised the whole transaction.
And that's the core issue here. Because all anyone needs to compute a hash value is the message body itself, we are totally blind to who actually created the message. We have zero authentication. We don't know if the sender was our highly secured, trusted billing server or a compromised machine operated by a hacker. A standard hash function protects you perfectly against a noisy, glitchy wire, but it provides absolutely no defense against an evil, compromised wire. To stop an active, intelligent attacker, basic hashing is simply not going to cut it.
So how do we fix this? Enter Section 4, Message Authentication Codes, or MAC.
To fix this massive vulnerability, we need to upgrade our toolset to something that guarantees both integrity and authenticity simultaneously. And the introduction of a secret key is the ultimate elegant fix. A Message Authentication Code, or MAC, fundamentally extends the hash concept. To compute a MAC, you don't just hash the message payload. You algorithmically mix the message with a highly secure secret key that is known strictly only to the authorized sender and the authorized receiver. Modern implementations do this using complex inner and outer padding to prevent advanced tampering. And because an intercepting hacker doesn't know the secret key, they can no longer forge the MAC. They can certainly still alter the message payload in transit, for sure, but they are utterly incapable of generating a mathematically valid MAC to go with it. Of course, this introduces a new challenge: key management. If that shared secret key is ever leaked or compromised, your entire authentication system falls apart immediately.
You can think of the MAC as acting exactly like a tamper-evident shipping tag appended to your message content. The sender generates the message, securely computes the MAC using the secret key, and attaches it as a tag. When the receiver gets the message, they do not just look at the tag. They take the raw message payload they received, retrieve their own heavily guarded copy of the secret key, and independently perform the exact same computation. If their locally computed MAC matches the tag that arrived on the message, the receiver absolutely trusts the sender. They know with mathematical certainty that the message was not altered in transit, and because only someone holding the secret key could have correctly formulated that tag, they know exactly who sent it.
Let's put this into practice with Section 5, Securing Data with HMAC.
Let's bring this to life. Imagine the Acme Corporation network. Acme staff members manually approve product refunds in a back-end warehouse application. This application then generates a refunds.json file and sends it across the internal network to the payment service. The payment service then issues real, hard currency back to customer credit cards based on the contents of this file. The stakes here couldn't be higher. If a hacker intercepts this file in transit and alters a $10 refund to become a $10,000 refund routed to their own account, Acme loses massive amounts of money instantly. The payment service must have an ironclad guarantee that this file came authentically from the warehouse service and wasn't altered by an attacker trying to steal funds.
This step-by-step handshake is the exact recipe that HMAC uses to completely lock down the transaction. First, the warehouse app computes an HMAC on the refunds file using a secure, shared cryptographic key. Second, it sends both the raw JSON file and the resulting HMAC tag over the network. Now, it is vital to emphasize here that the secret key itself is never, ever sent over the wire during this transaction. Third, the payment service takes the received file and independently computes its own HMAC using its own copy of that exact same secret key. Finally, the payment service compares its result with the tag it received. If they match identically, the file is validated and processed. If a hacker altered the refund amounts in transit, the HMAC computed by the payment service will fail to match the incoming tag. A security exception is thrown, and no fraudulent refunds are processed.
Now, there's a very famous, well-known industry maxim, don't roll your own crypto. Implementing your own cryptographic algorithms is incredibly dangerous and historically disastrous. Even if you understand the underlying math, custom implementations are highly susceptible to subtle flaws like timing attacks or side-channel attacks. This is where an attacker can actually guess your secret key just by measuring exactly how many milliseconds your algorithm takes to process different inputs. But the best news for you as a developer is that you don't need to write any of this complex math yourself. Standardized, peer-reviewed libraries like the Java Cryptography Architecture, or JCA, handle all the heavy lifting for you, safely padding the data and securely executing the algorithms.
Your main job isn't writing algorithms. It's simply picking the right tool for the job and configuring it properly. The JCA uses an elegant provider-based architecture. For the vast majority of applications, starting with the default JCA provider implementations that ship out of the box with OpenJDK is highly recommended. It's widely tested, highly reliable, and deeply secure. Later on, if your application scales to handle millions of transactions per second and you really need to squeeze out massive performance gains, well, then you can easily switch to non-default providers, like the Amazon Corretto crypto provider or Google's Conscript. These alternative providers utilize native C bindings and hardware-level CPU instructions to drastically accelerate cryptographic operations, saving massive amounts of compute cost, all without requiring you to rewrite your core application code.
Let's walk deliberately back through our mental rubric from the very beginning of this explainer. HMAC brilliantly secures integrity and authentication. It mathematically proves the data wasn't changed in transit, and it confirms exactly who sent it because only a trusted party possesses the secret key. But look closely at the third and fourth rows. It emphatically does not provide non-repudiation. Why? Because both the sender and the receiver possess the exact same shared secret key. If a dispute arises, the receiver cannot definitively prove to a judge that the sender created the message, because the receiver themselves has the technical capability to forge it using that same shared key. Achieving true non-repudiation requires asymmetric cryptography with public and private key pairs. Crucially, HMAC also does not provide confidentiality. Anyone intercepting the network traffic can still fully read the plaintext contents of the refunds file. They just can't alter it without getting caught.
So, HMAC is an incredibly powerful mechanism. It successfully elevates us from blindly trusting noisy wires to mathematically verifying both the integrity and the authenticity of every single byte of data flowing between our systems. But that leaves us with a fascinating final thought to ponder. If HMAC perfectly protects data from being secretly altered, but doesn't actually hide the sensitive contents of the message from prying eyes on a hostile network, how do we finally achieve complete confidentiality? How do we ensure that only the intended recipient can even read the message payload in the first place? Well, that is the complex domain of encryption, and it's exactly what you'll need to explore next on your journey into application security.